Hello students. In today's video, I'm going to discuss complex Fourier series. So far we have seen that any periodic function or a periodic extension of a function can be represented by a Fourier series. And this Fourier series is an infinite trigonometric series made of sine and cosine function. And this sine and cosine function, like sine of say nx or say cos of mx. These trigonometric functions shows the oscillation of fixed frequency. Now, similar to sine x and cos mx, if I write e power iota nx or e power minus iota mx, these function also shows fixed frequency oscillation. So by principle, we should be also able to write the Fourier series as a sum of exponential function. And when we write Fourier series as a sum of exponential function, then that is called complex Fourier series. So let us see how to approach. So if I have a function, a periodic function x plus b equal to fx, now uh, I can write and it is periodic extension is in the interval say c to c plus p. Okay, c plus p. Then what I can write? I can write the Fourier series for this function fx is equal to a naught upon 2 n equal to 1 infinite, and then you have an cos of 2 pi nx upon p plus bn sine 2 pi nx upon p. This is my Fourier series. And now if the interval is say minus L to L, if the interval is minus L to L, that is p is equal to 2L. Okay, if p is equal to 2L, then what will become? This becomes c plus 2L, and now c equal to minus L, then this period become minus L to L. For minus L to L, I can write the function a0 upon 2 n equal to 1 to infinite an cos, this is become 2L, so this become pi nxl or n pi xl plus bn sine n pi xl. This is my Fourier series for interval minus L to L and period 2L. Now, let us say we know my sine n pi xl can be represented as e power iota n pi x upon L minus e power minus iota n pi x upon L upon 2 iota. Similarly, we can write cos of n pi x upon L as e power iota n pi x upon L plus e power minus x upon L. This is my, now if I write my complex series, Fourier series, that is a0 by 2. Now you have an you have a e power iota cos n pi x upon L plus e power minus n L upon 2, and you have bn will be e power iota n pi x upon L minus e power minus L upon 2 iota. 2 iota. Now let me combine this series an terms, iota n pi xl terms, a0 by 2. Now this is my an by 2, and I want this term. Okay, so this term, if I multiply this by iota, okay, iota, so this become iota squared, this will become minus. Okay, this term become minus, so I can write an minus iota bn upon 2 is equal to e power iota n pi x upon n. Okay, and similarly here you have positive constant. You can also write the same series as n equal to 1 to infinite. Then you have a an, and now this minus can be written as the iota square. So iota iota cancels, so this becomes plus. So I plus iota bn upon 2 e power minus iota n pi xl. So now I write this as a, say, a0 by 2 plus n equal to 1 to infinite. I write this constant as a cn e power or coefficient as a cn pi x by l, and this coefficient, okay, I represent by, say, c minus n, c minus n e power minus iota n pi xl. Okay, now so you have a fx, which is a0 by 2 plus you have n equal to 1 to infinite cn e power iota n pi x upon l, and then you have plus, I'm separating, say, s equal to 1 to infinite c power minus n e power minus n pi x upon l. Okay, where cn is your a plus an minus iota bn by 2, and c minus, which is the complex conjugate of this function, cn an plus iota bn by 2. Now if I expand this series, I say this coefficient is c0. I say this a0 by 2 is c0, so this coefficient becomes c0. Okay, and you have here n equal to 1 to infinite cn c1 c2 iota and pi x upon l, and if you put n equal to 1 here, this becomes c minus 1, minus here minus 1, minus 1 here, minus 2, minus 3, minus 3. So this term is n equal to 1 to infinite c minus n and pi xl. Now I can combine these two, because now you have a 1 to infinite, and you have also minus 1 to this term. You put 1 minus 1 to minus infinite coefficient. Okay, so and here n is minus, so combine together these two summations including c0, I can write this as n minus infinite to n infinite cn exponential iota and pi xl. Now this contains 0 also. Okay, so if you minus infinite, it will come minus, and minus this term will come. If you say it's minus 5, c minus 5, and minus 5 iota 5 and pi xl. So this series contains these minus terms also, 0 also. If you put a here 0 here, this becomes c0, and then here you have these terms also. So this is my final expression for Fourier series or exponential Fourier series. And now same way, like we do in vector spaces, or property using the properties of orthogonal functions of exponential function, we can find now what we can find uh, Cn, like this coefficient Cn can be calculated if I integrate from minus L to L, and this function from minus L to L, this will give me minus L to L fx multiply e power minus iota and pi x upon L and divide by 2L. If we solve this one, you'll get the formula for Cn is total period L minus L 2L fx e power minus iota and pi xl. So this is my complex form of Fourier series. Now let us do one problem uh, solving complex Fourier theory. Say series, say I have given a function. Say I have given a function, say fx equal to x, and this interval is given, and this function is periodic. Okay, periodic function, periodic extension of the function f equal to fx. And now I want to write the complex Fourier series. Okay, so complex Fourier series for this function will be what? Fx n equal to minus infinite to infinite Cn exponential iota and pi x l. Now I want to find the coefficient Cn, which will, so you become now the series, this function is basically e power iota minus iota and x. Okay, because pi cancels. Okay, period is 2 pi, so this series becomes simple nx. Okay, so this becomes simply becomes nx. This becomes minus e power minus iota nx dx, and now we can integrate this one. So 1 upon 2 pi x e power minus iota nx minus iota n, and then you have, say, minus e power minus iota nx integrated twice square, and then you have limit minus pi to pi. Okay, and now this becomes 1 upon 2 pi. If you write here x, that will be pi e power iota and pi minus iota n minus e power minus iota and pi minus iota n square. Okay, and then you have minus pi. So minus pi, so minus minus will become plus, plus, and so you have a plus pi e power minus iota minus pi plus iota and pi, and you have a iota, and similarly this is also plus become plus minus pi iota and pi and minus iota and square is inside. Now if you solve this one, this gives me 1 upon 2 pi. So this term will be cancelled. This term will be cancelled. Okay. So this will be here. Okay. Here this is minus. Minus because I am putting minus pi, na? So this minus I'm keeping here as it is, because limit this pi and then minus and minus pi. So that become positive here. Okay. So this will be this will remain minus here. Okay. Minus here. So now, these two terms will be cancelled out and these two will be added. So you have Cn equal to 1 upon 2 pi. You have pi e power minus iota n pi 2, and then you have minus iota n. And now this can be written as a 2 pi cancel. This is iota square. So this will be iota e power minus iota n pi upon n. And this can be represented as a iota n e power minus iota n pi is minus, this is the sin pi 0, so cos n pi, and cos n pi is minus 1 power n. So finally I can say my coefficients, okay, my coefficients Cn, my coefficients Cn are minus 1 power n iota upon n, and my functions now becomes fx is equal to n minus 1 to infinity minus 1 upon n iota upon n e power iota nx. This is my function, but we have to check for c is equal to 0, because c0 has become infinite. So c0 we can calculate separately. C0 means only you have to calculate minus, so you have interval 2 pi, 2 pi, 2 pi fx dx. Fx is x dx. Okay, because exponential power c0 and 0 become 1, so this comes out 0. Okay, so this is the term when n is cn is equal to this, when n is not equal to 0, and for n equal to 0 your c0 is 0. Okay, so that while expanding this thing you have to write this one here. C0 is 0, and remaining n's you can write by this expression. This is the complex Fourier series of given function. Hope you understand the solution. Thank you very much.